Using VLANs is like breaking a physical switch into a few virtual ones. But eventually we'll need more physical ports, which means more physical switches. How do we get our VLANs to work across several switches? Like the many branches on a tree trunk, we can use a trunk link to carry many VLANs. Sound confusing? Hang around, it's all going to make sense soon. If the company we work for grows, then they're going to need more computers, printers, servers, and other devices. These all connect to the network, which means they all need more switch ports to connect to. So eventually we buy more switches. Normally we would connect one switch to another to extend our number of ports, but we've cut our network into VLANs now. So how do we connect the two switches together? Should we perhaps run a link between each switch for each VLAN? Well, we could. We could make that work. But what happens if we have many VLANs? If we need a link for each VLAN, we will use up our ports again pretty quickly, leaving less for the new devices that we need to connect. And then what happens if we want to add a third switch? Or a fourth? Clearly, this method is not scalable, meaning that its growth is severely limited. Instead, we are able to use a single link, which is capable of carrying all of our VLANs. This uses a technology called trunking or tagging. In the last video, we saw how to add devices to a VLAN. The type of port they connect to is called an access port. Typically, we would connect workstations, printers, servers, and phones to an access port. This will have one data VLAN, and maybe one additional VLAN for voice, which I'll talk about in a minute. When we connect two switches together, we configure these ports as trunk ports. Trunk ports are able to have many VLANs configured on them at one time. If you have trouble remembering the difference, an access port is how workstations access the network. Trunk ports are like a single tree trunk with many branches or VLANs. So we're left with an interesting question. Why do we want to use VLANs to separate traffic if a trunk link just mixes them all together again? Well, let me give you some good news. The traffic doesn't fully get mixed together. It goes over the same link, sure, but it won't leave its VLAN. This is thanks to our good friend Ethernet. As a reminder, here's the Ethernet header. Think of a device on a VLAN sending a frame. It goes to an access port, which is configured with a VLAN, so the switch knows which VLAN this frame belongs to. When the frame reaches the trunk link, the switch will add a 4-byte tag to the Ethernet header. The tag contains a few different types of information, but the only part we care about right now is the VLAN ID. Please note it's just the VLAN ID and not the VLAN name that we configured in the last lab. This means that VLAN names are locally significant to each switch and they don't have to match on two different switches. When the frame arrives at the destination trunk port, the switch looks at the tag and knows the VLAN that this frame belongs to. It can now strip the tag from the frame and deliver it to the destination workstation. So the workstation will never see the VLAN tag. In fact, it doesn't really even know that it's in a VLAN. And here is a key point for you. A trunk link extends VLANs from one switch to another. As VLANs are in a broadcast domain, trunk links also extend broadcast domains across switches. So broadcast messages will stay within a VLAN, but will pass over a trunk to other switches. And the same is true for flooding. Any frame that needs to be flooded will stay within the VLAN, but will travel over the trunk links to other switches. And once again, Cisco's terminology is a little bit different to everyone else's. To start with, a trunk port is really a tagged port. This is because of the tag that is added to the frame as it passes between the switches. Also, an access port is really an untagged port. Remember how I said that there is no tag in the Ethernet frame when it was delivered to the workstation? That's why it's called an untagged port. Don't worry too much about which terminology you use. They're both really well known. It's still a good idea to understand both, so you'll always know what other people are talking about though. When it comes to tagging, there are two ways it can be done. The first is called 802.1q, which was developed by the IEEE. Everyone supports this standard, and this is what I've been describing so far. Because this is an IEEE standard, all switches can use it, which means a trunk between switches from different manufacturers is possible. The second possibility is called ISL, or Inter-Switch Link. This is Cisco's original trunking standard and is much older than 802.1q. This one's getting pretty rare these days. In fact, I've never actually seen it in production myself. But you do still see it mentioned in some documentation, and you can still configure it on some switches, so you need to be aware that it's out there. But in most cases, forget ISL and focus on 802.1q. Earlier, I mentioned voice VLANs. These are important if you have IP telephony in your network. If you're not familiar with that term, IP telephony is where you have phones connected to your network. In a case like this, you would probably have a phone and a workstation on each desk. Your workstation would belong to a data VLAN, while the phone would belong to a voice VLAN. So based on what we've talked about so far, you would probably connect the workstation to one port on the switch, and the phone to another. But usually, phones are a little bit special. They have a miniature 3-port switch built in, so we can connect the phone to the switch, and the workstation to the phone. The third port is hidden from sight, it's inside the phone, connecting to the phone hardware. Why would we do this? Well, there's two reasons. For one, there's less need for ports in the main switch. Secondly, you don't normally connect phones and workstations directly into a switch. They normally go into a wall socket, with cabling through the wall, which is eventually connected to the switch. So with less connections to the switch, there's less need for cabling, which can be expensive to install. Anyway, the link from the phone to the switch is like a mini trunk link, except it carries only two VLANs, the data VLAN and the voice VLAN. We'll have a go at configuring this later. Voice networking is a subject entirely of its own, so we're not going to get any deeper into voice than that though. Right, let's try some of this in the lab. Our topology is very similar to the last video. In fact, logically, it's the same network. However, you'll see some differences in the physical topology. We've now added an extra switch, which will mean configuring a trunk link. We've also removed a physical link from the router, and we'll see what that's all about a bit later on. I hope this helps to explain why we have logical and physical diagrams. We can make changes to the way the network is physically deployed without really changing the logical components of the network itself. So, the basic config from the last video is still there. From the point of view of the workstations, not much has changed. We do have two switches now, and one workstation and one server have been moved to the second switch. I've already moved the config for these ports to the second switch, so you won't need to worry about that. And just for a quick review, this is how the workstation ports are configured. It's very simple. Just one line to put them in the right VLAN. These are access ports, which I hope makes a bit more sense to you now after a bit of an explanation than it did in the last video. But access ports aren't the only option we have. Another possibility is to configure a port with a voice VLAN. Unfortunately, I don't actually have a VoIP phone to connect to this lab, but we're going to pretend that we do, and we'll configure the port just like we normally would. So we'll start by configuring VLAN 110, and we'll give it the name voice. This is exactly the same as before, there's no fancy configuration here. Next, we configure our interface. As I said before, it's not connected to anything, but you'll get the idea. First, I'm going to force this port to be in access mode. Switch ports have the ability to dynamically decide what port type they are, so forcing it is kind of optional. The way the dynamic nature works is a bit advanced for now, so I'm not going to explain that just yet, but the short of it is I like to set the ports manually. This is especially useful if other people have been working on the switch and may have changed the default values. We can now set the voice VLAN. This still uses the switch port command, so this should be quite comfortable. Sorry, I've done that wrong. That should be in VLAN 110. And finally, we set the access port as well. So keep in mind that when you have a phone connected, you set the voice VLAN as well as a separate access VLAN. Now, let's get back to that trunk link. We haven't configured it yet, so as you would imagine, if we jump onto workstation 1 and we try to ping workstation 2, it's going to fail. So for this to work, we need to configure a link that allows us to add VLAN tags to the frames that will pass between the switches. The good news is, it's not really difficult to do at all. Let's start over at switch 1 and enter into interface configuration mode. The first step is to set the encapsulation type. There are 3 options we could configure, which are .1q, ISL, and negotiate. Negotiate is that dynamic port type that I was talking about earlier, so we'll ignore that for now. Of the other 2 options, we want to use .1q, which is the most common form of tagging. Now we need to configure the port type. Previously, we've configured access ports, but on this occasion, we're going to use a trunk port. Remember that a trunk port allows frames to be tagged with a VLAN ID. We need to do the same over on switch 2. I've made switch 2's CLI look purple, so it's easy to tell which switch is which, so I hope that doesn't hurt your eyes too much. When we configure trunk links, we have the option of allowing some VLANs while disallowing others. This is called pruning, and we do this with the switch port trunk allowed VLAN command. If we don't use this command, all VLANs are allowed over the link. If we do use this command, only the VLANs in this list are allowed. We don't really need it for what we're doing today, but you will see other people doing this regularly, which is why I wanted to mention it. There's a few things that we should do to make sure that we've been successful. Show interfaces switch port is one of the commands we can use, and it gives us a lot of information. But before we dig into this, let me just show you a quick trick. When a command gives you too much information, there's an extra CLI command that you can use to filter this down a bit. After you type your command, enter the pipe symbol. Next, we're going to use an extra command called begin. This will look for whatever pattern you give it, and it will start displaying the output from that point forward. So we'll use begin gi0/2. This will start the output at the point where gi0/2 first shows up. Pretty neat, huh? So in this output, there are a few points of interest. First, we can see the port type. In our case, it's a trunk port. We can also see the type of encapsulation that we're using, as well as the VLANs that are allowed over the link. Another command we can use is show interfaces trunk. For a trunk port, this gives us similar information, but is a little bit tidier. You should know though that this is only for trunk ports, as the name suggests, so access ports won't show up here. But the best way to prove that this is working is to head over to workstation 1. From here, we can see that traffic is successfully flowing across the trunk link to workstation 2. So do you understand what's going on? Find out by testing yourself with this quiz. If you have any questions, let me know in the comments. When you first turn on a switch, all the ports will, by default, belong to VLAN 1. We don't do anything to configure VLAN 1, it's just always there. So is VLAN 1 special in any way? The answer is a little bit tricky, but on a Cisco switch, VLAN 1 is indeed a little bit special. From time to time, there is a need to pass control traffic between devices. So I'm not talking about a workstation sending traffic through a switch here. I'm talking about a case when two switches are connected together, like in our lab. We're going to see this a bit later on with an example protocol called CDP. But the key point here is that control traffic between Cisco switches use VLAN 1. Keep in mind that other switch vendors may have a different way of approaching this. So don't try to remove VLAN 1. I don't even think you can remove VLAN 1 now I think about it. Also, it's a good practice to keep your devices, like your workstations and printers and so on a separate VLAN. Just leave VLAN 1 for this control traffic. There's another special VLAN that we need to consider. This is called the native VLAN. The native VLAN was created to support devices that don't support VLANs. Think of a hub or a cheap switch, for example. If you connect one of these devices to a trunk link, they won't be able to tag any of the traffic they send. So which VLAN is this traffic a part of? The answer is the native VLAN. By default, the native VLAN is VLAN 1, but we can change this to another VLAN if we want to. In fact, we'll see this in a lab soon. But before that, consider what happens if traffic passes from a switch to a hub. Any frames that are part of the native VLAN will be sent out untagged. This keeps compatibility with these non-VLAN enabled devices. Time to head back over to the lab. This is the same one from before, so there's no surprises. We can show a VLAN summary to see how many VLANs have been configured on this switch. This doesn't give us a lot of information though, so I prefer to use show VLAN brief. Now see how VLAN 1 is there, even though we didn't configure it? VLAN 1 is always there by default on Cisco switches. If we have a look at an unused port using our show interface switch port command, we can see that it's already in VLAN 1. All ports on a Cisco switch are in VLAN 1 by default. Looking at our trunk link, we can also see that VLAN 1 is the native VLAN. This is also how Cisco switches are configured by default. But it doesn't have to be that way. We can set the native VLAN to nearly any number we want. Under interface configuration mode, we can use the switch port trunk command to change trunking parameters. For example, we could change the native VLAN to be VLAN 2. Although we're not seeing any problems here, this will eventually generate some warning messages. This will happen because switch 2 is still using VLAN 1 as its native VLAN. While it's not mandatory, it is a good idea to have both switches use the same native VLAN. For now though, we'll just put it back to VLAN 1. But how do the two switches know that there's a mismatch? How does one switch know how the other is configured? It does this by using a protocol called CDP, or Cisco Discovery Protocol. This is one of those types of traffic that flows between the switches themselves and will always use VLAN 1. This is a little bit off topic, but I think it's worth a quick look. So CDP is a Cisco-made protocol. If two devices that are connected together support it, they can learn about each other. On most Cisco switches, it is enabled by default, which we can confirm with show CDP. This is not too exciting, so let's try show CDP neighbors. Here we can see that we've learned about switch 2 on interface GI0/2. It also mentions GI0/0, which is just something that my lab software does, so don't worry about that one for today. When we add the detail keyword, we get a ton of more information. For example, we can see the native VLAN, and that's how they detect that mismatch. We can also see the iOS version that the connected device is running. An interesting point is the capabilities section. This tells us what features our switch thinks the connected device is capable of. If we really wanted to, we could disable CDP with no CDP run. Some people like to do this for security reasons, which is quite understandable. This can be done globally, like we've just done, or we could disable it on some individual ports while leaving it active on others. And of course, we can enable it again with CDP run. So why do we use CDP? Well, it helps with troubleshooting the network and is particularly useful if you haven't been keeping your network documentation up to date. Also, if you're connecting Cisco phones, CDP will help you to set up your voice network. But as I said, this is a Cisco protocol. They made this years ago when there were no other options. So what happens when you connect a device made by another manufacturer? Well, some other vendors, like VMware, they do support CDP, but a lot of vendors don't. Fortunately, there is an alternative called Lldp, or Link Layer Discovery Protocol. Lldp is vendor neutral, so it's supported by a lot of vendors as well as Cisco, and it does the same basic job as CDP. Just as with CDP, we can enable or disable it globally or per interface. It's disabled by default on this model of switch, so we'll need to head over to switch 2 and enable it there. If we're particularly security conscious, we can configure interfaces to only send or receive Lldp traffic. But we'll leave it all turned on for now. Lldp commands are basically the same as CDP, and the output is very similar too. So just to see if you're following along, here's a few more quiz questions that you can try. See how you go. Now, in the last video, we connected a router to each VLAN to enable workstations and servers to communicate. There were 2 VLANs, so we used 2 links. But what if we have 10 VLANs? Do we need 10 ports on our router? Does our router even have 10 ports? What if we needed 30 VLANs? This is the same concern we faced with our switches earlier. We solved this by using a trunk link. The good news is that routers can also use trunk links. This might sound surprising, as trunking is a switching technology, but you'll find that the lines between routers and switches are sometimes blurry. Routers will support some switching functions, like trunking, and switches will support some routing functions too. But they still behave a little bit differently. Routers primarily deal with routing, which means their interfaces need IP addresses. This is what the workstations and servers will use as their default gateway. But how can we put an IP address in each VLAN? How does the router know which IP address belongs in each VLAN? The answer may surprise you. The router's physical interface is connected to the switch, but the physical interface can be divided up into several virtual sub-interfaces. This is very similar to how we divided our switch into several VLANs. On a router, we divide up interfaces and we map each one to a different VLAN. And once we have several virtual interfaces, we configure them independently. This includes different IPs for each one. And these interfaces, even though they're virtual, still behave like regular interfaces, so we can still use them to route traffic between VLANs. This way of configuring the router is called Router on a Stick, or ROAS. It's called this because the single trunk link between the router and switch looks a bit like a stick. Maybe it's easy to see this in action. Back to the lab we go. We need to configure the router's port as a trunk too. This uses the same concepts, but the commands are a little different. Step 1 is to make sure that the physical port is up with the no-shut command. Next, we create our first sub-interface. This is done by entering interface configuration mode using the physical interface's name, followed by a dot, and then a number. I always use the VLAN ID as the number, as it makes it easier later on. Under interface configuration, we now set the encapsulation type to 802.1q, so it matches our switch. We also need to include the VLAN ID. And once that's done, we configure the rest of the interface just like we would for any other interface, which includes setting an IP address and, if we wanted to, a description. Of course, we now need to repeat the process for a sub-interface on VLAN 20. The IP addresses that we're adding to the sub-interfaces are the default gateways that the workstations and servers are using. Now we can go and confirm it's working over on workstation 1. Let's start by pinging the router's sub-interface. And that looks good, so now we can try pinging a server in VLAN 20. This also looks good. And finally, just to prove that there's no trickery going on, we can run a trace route to confirm that the traffic is going through the router. And that's the lab configuration done. I highly recommend that you try this yourself. Either build your own lab or download the one I've pre-built for you. And of course, try to answer the quiz questions to check your understanding. We've now covered the basics of VLANs, including how they work and why we use them. You will see them a lot, so get as familiar as you can with them. We're going to step it up in the next video and see how we can limit the traffic between our two VLANs using the router. I hope to see you there.